Good morning dear students, my name is Ajit Singh Rawat and I am a mathematics teacher. Today I will be taking up the topic of class 12, the three-dimensional geometry, and in three-dimensional geometry we have two subtopics. One is the straight line and another is a plane. This straight line and plane will study these two things in space, three-dimensional space. So let me first introduce what is a plane. For this, I have this right circular cone with me, and as you can see, this surface, you might have studied in class 10 that this is known as the curved surface area. The surface I am touching right now is known as the curved surface area, and the bottom, this is also a surface, right? So out of these two surfaces, you see this surface, it is not a plane, right? But this surface is a plane. So what is the precise definition of a plane? It is a surface is a plane if I join any 2 points on that surface, and the line joining the 2 points, if it entirely lies on that surface is known as a plane. Just imagine we have a say point here and we have a point here. So just imagine a line passing through these 2 points. So you will see this line will pierce through this solid, and this line will not lie on this surface. So this surface is not a plane. On the other hand, if on this surface I take any 2 points and I join them, you can see the line entirely it lies on this surface. So this is the definition of plane. Okay, so we in daily life we have so many examples of plane, like this board, this whiteboard is also a plane. The surface, this floor is also a plane. The walls are also a plane. This thing is also a plane, right? And it's not like it has the boundary, but it can be extended in any direction infinitely. So plane is not limited to this, but it can be extended in any direction. This is the plane. So now we know the definition of a plane, what surface is a plane. Now we try to fix a plane in space. We see how many conditions we need to fix a plane in three-dimensional geometry. So before starting plane in 3D, I would like you to ask few questions in two-dimensional geometry so that we can relate that thing with three-dimensional geometry, right? So come to two-dimensional geometry where we have these two axes, x-axis and y-axis, and we have a point, right? So just tell me how many lines can pass through this point. So your answer is infinite lines can pass through this point. It means if I just give you one point, you cannot fix the line in two-dimensional geometry, right? But with a point I give you slope, a line which passes through this point and which is having slope say 1. So in that case it will be this line which will make angle 45 degree and also passes through this point. So now the line is fixed in 2D. So this is how we fix the line. And suppose we have again, now we have 2 points, 2 distinct points in two-dimensional geometry. The line passing through these 2 points will also be a unique line. Only one line can pass through 2 distinct points in two-dimensional geometry. So now the line is fixed. With 1 point the line is not fixed. With 1 point you need slope to fix a line. If you have 2 points, then also the line is fixed. And there are so many other conditions to fix a line in two-dimensional geometry, right? But similarly in three-dimensional geometry. Now to fix a plane in space, again we see, suppose say the tip of my finger is a point in space and plane passes through this point, right? So can we have a unique plane through this point? No. We have this plane, we have this plane, we have this plane. There can be so many planes passing through this point in. So one point cannot fix a plane in space, right? Now imagine 2 points. Suppose we have 2 points. Say this is 1 point in space, this is another point in space, and now we have this plane passing through these 2 points, right? But we have more such planes. You can see this is also a plane which passes through these 2 points. This is also a plane which passes through these 2 points. There are again infinite planes passing through these 2 points in space. So now suppose we have 3 points in space that are not collinear, means they do not lie on the same straight line, otherwise the same situation will be there. You have these 3 points, and again we have so many planes passing through these 3 collinear points. So if we have 3 collinear points, the plane is not fixed. But if we have 3 non-collinear points, it means the points in space which do not lie on a same straight line, then just imagine we will have a unique plane. No 2 planes can pass through 3 non-collinear points in space. So one way of fixing a plane is 3 non-collinear points, then a unique plane will pass through those 3 non-collinear points, right? There are some more situations by which we can fix a plane in space. Another is, just imagine a plane passing through this point, okay? There can be so many planes, but if I fix the direction of the normal to the plane. Now what is the normal to the plane? This is a surface, this is the direction which is normal to the plane. This is also a direction which is normal to the plane. So any direction which is perpendicular to the surface of plane, we will call it a normal to a plane. So suppose if a plane passes through this point but the normal is having this direction. So now you cannot do like this, right? Because direction of normal is fixed. So these 2 things are, you can say these 2 conditions are enough to fix a point in space. So 3 non-collinear points can fix a plane in space, a point and the direction of normal can fix a point in space. And one more thing is, say suppose, one more situation is, this is our space, this is our origin, and suppose we have this, the direction of normal of course, and the direction of the normal is suppose like this. So we have all these planes, normal is in this direction. So how we are going to fix it? Now if we fix the distance of the plane from origin, that the distance of this plane from origin is 5, now we cannot do it like this. So again a plane is fixed. So what I have told you is, if there are 3 non-collinear points in space, a plane is fixed in space. If I have a point through which the plane passes and the direction of normal, then the plane is fixed. And if I have the normal vector and the distance of the plane from the origin, then also a plane is uniquely determined. So NCERT book starts with this thing only. When you start studying NCERT book, the topic plane, firstly you will see these 3 important points, how to fix a plane in space. So a plane is determined. Determined means how to fix a plane in space. A plane is determined uniquely. It means we have one and only one plane, unique plane, if any of the following conditions are known. First is the normal and the distance of that plane from origin. If these 2 things are there, we can find the equation of plane. If it passes through a point, a passing point and the perpendicular direction, then also a plane is fixed in space. And finally, if we have 3 non-collinear points, then also we can fix the plane. In the coming next few articles, you will be discussing these forms one by one in detail. So next we have the equation of a plane passing through a given point and perpendicular to a given vector. So next we have the equation of a plane. Say suppose this is a plane which passes through this point, say A, with position vector A vector. So there is a plane which passes through point A, point is given to us, and also a vector is given which is perpendicular to the plane. So say n vector be the vector which is perpendicular to this plane. So it will be something like this. Say this is a point through which the plane passes, and we also have a vector which is perpendicular to the plane. So these 2 conditions are enough to find the equation of the plane. So let us see how. So for finding the equation of the plane, say consider a point P, any point P on the plane with position vector r vector. So A is the fixed point through which the plane passes, and P is any point on the plane. So clearly we will be using this condition of perpendicularity, reason being this is the vector which is normal to the plane. So if you want to use the condition of perpendicularity, we'll be needing a vector which is perpendicular to this vector n. So you can see, suppose now this vector, AP vector, since the point A and P are on the plane, so this AP vector will lie on the plane. So we have a vector which is lying on the plane, and we have a vector which is normal to the plane. It means these two vectors are perpendicular. So the dot product of these two vectors will be 0. So dot product of this vector with the normal vector will be equal to 0. Reason being they are perpendicular. AP vector is the position vector of point P, that is R, minus position vector of the initial point A. So this is AP vector, and dot n vector is equal to 0. So from here we have R dot n minus A dot n is equal to 0. We have this passing point, it means we have this A vector and we also have this normal vector. So this is a scalar you can easily calculate. So R dot n is equal to this scalar will go to the other side and call it lambda. So this is the required equation of the plane in vector form. Okay, and suppose we want to find the equation of the plane in Cartesian form. So from here R vector is a position vector of any point. So let this point, any point, be x, y, z, and A vector is a position vector of the passing point. Let the passing point be x1, y1, z1, and let the normal vector has the direction ratio A, B and C. So from here what I get is xi plus yj plus zk minus A vector, that is x1i plus y1j plus z1k dot n vector. N vector will be ai plus bj plus ck, and this will be equal to 0. So the difference of these two vectors is x minus x1, and when we do the dot product, this will be A times x minus x1 plus B times, from here we have y minus y1 plus C times we have z minus z1 equal to 0. So this is your equation of plane in Cartesian form. So in both these forms, this is very important form of plane. Whenever we want to find the equation of a plane, we will be looking for a point through which the plane passes, and if we have a vector which is normal to the plane, we can always write the equation of that plane using this form. So this is the very important form of plane. Next, to understand this form, let us take an example in which we need to find the vector and the Cartesian equation of a plane which passes through this point 5, 2, minus 4 and is perpendicular to a line with direction ratios 2, 3, minus 1. So to understand the situation, let us draw a rough diagram. So suppose we are trying to find the equation of a plane which passes through the point 5, 2, minus 4. This is the point through which the plane passes, and we have a line which is perpendicular to this plane, and the direction ratios of this line are 2, 3, minus 1. So how we are going to find the equation of this plane? We need not do the whole article, the whole concept, but we will simply using the formulas, the forms which we have derived earlier. So for solution part, to write the equation of such plane, we can use this form. Equal to 0. So you remember this. This is the equation of a plane which passes through the point x1, y1, z1. So the passing point is given. So this is the passing point x1, y1, z1. And what were A, B and C? A, B and C were the direction ratios of a vector which is normal to the plane. So this line is also perpendicular to the plane. So the direction ratios of this line can be used for the values of A, B and C. So we have the values of A, B and C, and we have the value of the passing point x1, y1, z1. We can write the equation of such plane. So from here we have x minus x1, that is 5, B 3 times y minus y1, that is 2, and C times, that is minus 1 times z minus z1, that is minus 4, equal to 0. So this is 2x plus 3y minus z, and then we have minus 10 minus 6, this is plus 4, again minus 4, equal to 0. So the equation of this plane is this. This is the Cartesian equation of the plane. Here we also have to find the vector equation of the plane. So you must know how to convert from vector form to Cartesian form and Cartesian form to vector form. So for this we can write, for x, y, z we can have this r vector, then dot with 2y plus 3j minus k equal to 20. So this is the vector, this is the Cartesian, this is the Cartesian equation of the plane, and this is the vector equation of the plane, required plane. Next form of plane is the equation of a plane passing through 3 non-collinear points. So we have 3 non-collinear points in space. Reason being the points should be non-collinear is because, suppose just imagine we have 3 points, say these are the 3 points, right, which are collinear. So you can clearly see this is a plane passing through these 3 points, this is also a plane passing through these 3 points. So in fact the plane will not be fixed in the space. So if the points are collinear, there is a problem, the plane is not uniquely determined. But if we have points, say just imagine these 2 points and this point, the 3 points in space which are not collinear, then we have a plane, a unique plane passing through 3 non-collinear points. So that is why we must have 3 points which are non-collinear. They must not lie on a same straight line. So we will now try to find the equation of such plane. So we have 3 non-collinear points, say A, B and C. A, B, C are 3 points, non-collinear points in space, and this is a plane which passes through these 3 non-collinear points. And say these points have position vector A vector, B vector and C vector, and we need to find the equation of a plane. For that, let us assume an arbitrary point P having position vector R vector. So R vector is any point on the plane. A, B, C points are non-collinear, fixed through which the plane passes, but this point P is any point on the plane. So in the last form, what I explained was, you will be needing a vector which is normal to the plane, and you will be needing a point through which plane passes. We already need one point through which the plane passes. Here we have 3 points through which plane passes. So point is not a problem. How we are going to find a vector which is normal to this plane? So for that we will be using the concept of cross product. In vectors chapter you might have studied, suppose say this is vector A, this is vector B. These 2 vectors are lying on this plane of this whiteboard. So A cross B vector, the vector A vector cross B vector will be a vector which is, you can obtain that vector by using right hand curl rule. It will be a vector which is perpendicular to both A and B, right? And also we can say that this is a vector which is perpendicular to the plane containing A vector and B vector. So in this way we will be generating a vector which is normal to the plane. So for that we will be needing 2 vectors, this vector and this vector. Since A, B, C lie on the plane, so AB vector and AC vector, AB vector and AC vector, these 2 vectors will lie on the plane. So when I take cross product of these 2 vectors, I will be getting a vector which is normal to the plane. So this vector for me can work as a normal vector, and we can use any point, say A. So you can use this form, r minus a dot n equal to 0, right? And instead of n vector, since we do not have n vector here, but we can find a normal vector to the plane by AB vector. Now what is AB vector? It is B minus A cross AC vector, it is C minus A. So when we take dot product of r minus a vector with this normal vector, the dot product will be 0. This is the vector equation of a plane passing through three non-collinear points having position vector A vector, B vector and C vector. This is the equation of plane in vector form. And for Cartesian form, we can assume the first point x1, y1, z1, the second point x2, y2, z2, the third point x3, y3, z3, and the arbitrary point x, y, z. So for Cartesian, for finding the equation of such plane in Cartesian form, we can simply subtract the vectors, find the cross product and finally do the dot product. It comes out to be equal to this determinant. You can understand this by the concept of scalar triple product also. These are the three vectors and this is the scalar triple product of these three vectors. So in this determinant, in the first row we have the components I component, j component and the k component of this vector. So x minus x1, y minus y1, z minus z1. So you can simplify this also and you can also use the concept of scalar triple product. So for Cartesian form, you need to evaluate this determinant. And for the second row, we have the components of this vector. So x2 minus x1, y2 minus y1 and z2 minus z1. And for the third row, we have this. So if this is the straightaway direct form in which the question is like find equation of a plane passing through this point and this point. Very straightforward question. So you can simply call the first point x1, y1, z1, the second point x2, y2, z2, the third one x3, y3, z3. Evaluate this determinant to get the equation in Cartesian form. Then also you can convert it in vector form. So it is not necessary that you remember this form. Either you remember this or you remember this. And later on you can always convert the equation from one form to another, right? So a simple problem based on this form of equation of plane. We have to find the equation of a plane which passes through these three given non-collinear points. So you have the result. You need not do the complete article. You can simply use this r minus a dot b minus a cross c minus a equal to 0. So if you have to memorize this result in order to do this question, or there is one more way, you can also solve it in Cartesian form. For that you need to remember this determinant. So either you go by the vector method, these three will be the components of a vector, b vector and similarly the c vector, and in Cartesian form we have this determinant x minus x1, y minus y1, z minus z1, where x1, y1, z1, this is x1, this is y1, this is z1, this is x2, this is y2, this is z2, and the third point x3, y3, z3. So you need to remember this determinant. You can simply put the values and get the required equation of plane. So this determinant you have to memorize it: x2 minus x1, y2 minus y1, z2 minus z1, then x3 minus x1, y3 minus y1 and z3 minus z1. So either use the vector form or the Cartesian form to find the required equation of plane. So very straightforward, direct question, and important one also. It is often asked in your board exam. So moving on to the next topic. Next we have the equation of plane in intercept form. So suppose this is our three-dimensional geometry. This is x-axis, y-axis and z-axis, and we have our plane like this. So this is the plane. So this is the x-intercept A, made by the plane on x-axis. Similarly, on y-axis, the intercept made by the plane, say it is B, and on z-axis this is C. So A, B and C are the intercepts made by the plane on the three mutually perpendicular axes, that is x-axis, y-axis and z-axis. So we'll try to find the equation of the plane when these intercepts are given to us. So if say x-intercept is given, actually we know this point, right? Since it is a point a distance away from the origin, so the coordinates of this point are going to be a, 0, 0. This distance is b and this point is on y-axis, so this point is 0, b, 0, and similarly this point will be 0, 0, c. So actually we now know the 3 points on this plane, 3 non-collinear points in this plane. So using the previous article, we can write the equation of this plane using the 3-point form of equation of plane, which was x minus x1, y minus y1, z minus z1, x2 minus x1, y2 minus y1, z2 minus z1, x3 minus x1, y3 minus y1, z3 minus z1. So take this first point A as x1, y1, z1, this point B say x2, y2, z2, and this point C as x3, y3, z3. Since we know 3 points on the plane, so using the 3-point form of equation of plane, we can write its equation. So putting the values, so now x1 is a, y minus y1, y1 is 0, z minus z1 is again 0. Then we have x2 minus x1, 0 minus a, y2 minus y1, y2 minus y1, d minus 0. Then we have z2 minus z1, that is 0 minus 0 is 0. Then we have x3 minus x1, that is 0 minus a, y3 minus y1, y3 that is 0 minus y1, 0 minus 0 is 0, and at last we have z3, that is c minus 0. So this is x minus a, y, z, minus a, b, 0, minus a, 0, c equal to 0. So expanding this determinant along row 1, we have x minus a times bc minus 0 minus y times, you delete this row and column, minus ac minus 0, and finally z times 0 minus ab, that is ab equal to 0. So we have bcx minus abc plus acy plus abz equal to 0. So we can arrange the terms, and in fact we can divide this equation by abc. So abc, 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 abc. So we have x upon a minus 1 plus y upon b plus z upon c equal to 0. Change this term to, take this term to other side. So we have equation of plane in intercept form. The form is x by a, y by b plus z by c is equal to 1. So remember this result. So if we have the intercepts ABC, then we can write the equation of that plane directly using this form. X by the x-intercept, y upon the y-intercept, z upon the z-intercept. Please note, this ABC is not, these are not the direction ratios of the normal to the plane, but in this form ABC are the intercepts made by the plane on the coordinate axis. So a simple question based on this form, the intercept form of equation of plane, is For 1 or 2 marks it can be asked. Find the equation of a plane with intercepts 2, 3, 4 on the x-axis, y-axis and z-axis respectively. So you will be using simply this form. This is the intercept form for the equation of plane, and these are the intercepts ABC. So x upon 2 plus y upon 3 plus z upon 4 equal to 1. This is the equation of the plane having intercepts 2, 3 and 4. You can simplify this also. So for that you can take 12 LCM. So 6x plus 4y plus 3z is equal to 12. And if you want to convert, if the question is find the say vector equation, so still you can do it like this, and in the final step what you can do is for x, y, z you can write r vector. For normal vector you can write 6i plus 4j plus 3k equal to 12. So if you want your answer in vector form, you can convert from Cartesian to vector form, right? Next is the equation of plane in normal form. To write an equation of plane in normal form, we need two things, two basic things. One is the distance d of the plane from origin, and another is a unit vector which is normal to the plane. N cap is a unit vector normal to the plane. So if the direction of normal is given, that is fixed, and if the distance of the plane from origin is fixed, that plane is uniquely determined, right? It means the plane is fixed in space. Now we will try to find the equation of such plane. So the two things which are given to us is, the one thing is the distance of the origin from the plane. So let OM be the distance d of the plane from origin, and again we have the direction n cap which is normal to the plane. So n cap is the direction which is again perpendicular to the normal to the plane. So these two things fix the plane in space. Now we will try to find its equation. For finding the equation of plane, consider an arbitrary point P, any point P on the plane with position vector r vector. And now, like we did in the another form of equation of plane, again we will find a vector in which lie on the plane, and we have a vector which is normal to the plane, and we will be using the condition of perpendicularity, that when two vectors are perpendicular, their dot product is equal to 0. So that will help us to find the equation of such plane. So any vector, if we join this point P with this point M, right? This point P with this point M, this MP vector is a vector which lies on the plane, and its dot product with n cap is going to be equal to 0. Reason being, they are perpendicular. For finding MP vector, we need the position vector of M. Reason being, MP vector will be position vector of the terminal point P minus the position vector of the initial point M. You might have studied this in vector. MP vector, for MP vector, we need position vector of P. Position of vector of P is no problem. It is R vector. What is the position vector of M? Position vector of M means this OM vector. Position vector of M means OM vector. OM vector, the magnitude of OM vector is known to us. It is D, and the direction of this OM vector will be same as the direction of n cap. So we will be using the direction of the normal vector for this finding this vector, the direction of OM vector. Reason being, distance is always measured perpendicularly. This direction is also perpendicular to the plane. This distance is also perpendicular to the plane. So same direction can be used for OM vector also. So OM vector, the magnitude is D and the direction is that of n cap. So OM vector is, the position vector of OM, that is OM vector, is D n cap. So now we will make the dot product of these two vectors equal to 0. From here we have r vector dot n cap minus d n cap dot n cap is equal to d. N cap dot n cap, You know I cap dot I cap is 1, j cap dot j cap is 1. Similarly, n cap dot n cap will be equal to 1. So we have r vector dot n cap. You can change the side of this is 1, this is d, minus d. Take it to that side, it is d. So this is the vector form. This is the vector form of equation of plane in normal form. Reason being, we here n cap, always remember in the form what is n cap and what is d. If this is a unit vector, right? If it is a normal vector, then this will not be a perpendicular distance of the plane from origin. But if we have this vector as a normal unit vector, then this d will be the distance of the plane from origin. If we try to write this equation in Cartesian form, so the direction of n vectors is say ABC. ABC be the direction ratios. In fact, for unit vector we have not direction ratios, we have the direction cosines. So n vector is Li plus Mj plus Nk, and r vector, as you know, is Xi plus Yj plus Zk. Their dot product is equal to d. So we have the Cartesian form as Lx plus My plus Nz is equal to d. This is the Cartesian form. Always remember, L, M, N are the direction cosines, not the direction ratios, but the direction cosines of the normal unit vector, and d is the distance of the plane from origin. Moving on to the problem based on the normal form of equation of plane, we have to find the equation of a plane which is at a distance of 2 units from the origin. It means d is given. The distance of the plane from origin is given 2. And the normal vector from origin is this. This is the normal vector. This is the normal vector. From the magnitude, you can find out whether it is a normal unit vector or just a normal vector. So the magnitude of this vector is square root of 2 square plus minus 1 square plus 2 square. That is square root of 4 plus 1 plus 4. It is square root of 9, that is 3. So this vector, from the magnitude, you can say this is not the normal unit vector, right? It is a normal vector, not a normal unit vector. So if we use the normal form, that is r vector dot n cap is equal to d, we have the distance of the plane from origin. But for finding the unit normal vector, you have to divide this normal vector by its magnitude. As you know, a normal unit vector can be obtained if we divide the normal vector with its magnitude. So this will be 2 by 3 I minus 1 by 3 j plus 2 by 3 k. So this is the normal unit vector. So the equation of the plane is r vector dot 2 by 3 I cap minus 1 by 3 j cap plus 2 by 3 k cap is equal to 2. So this is the vector equation of the plane which is at a distance of 2 units from the origin, and this was the normal vector. But if you want to use the normal form of the equation of plane, we have to convert it into the normal unit vector.